Hello everyone. So, we will continue with the tensile testing, and today we will start with the beam balance principle. Okay. First, let us see what is the principle of measurement of tensile characteristics by beam balance. This is the basic principle. Here it is a beam AB, okay, where it is a pivoted at point C. Now, if we want to know the force, okay, the load on the specimen P, we can calculate the load on the specimen P by knowing the force applied, downward force applied at point F, A, that F force applied, and if we know the distance. So, BC is the distance from the pivot point to the specimen, and AC is the distance from the pivot point to the force applying point. Okay. So, this is the equation, simple beam balance equation, P multiplied by BC equal to F multiplied by AC. So, the load on the specimen P can be varied, okay, by changing the F. So, this is the load. So, if we change gradually, if we change the load, that means the P value can be changed, so that we can measure the strength, okay, up to the breaking point, or by changing the distance, that is distance from the fulcrum point C. So, that loading point, if the load is constant, so either we can change the load F keeping the this AC distance fixed, okay, then we can change the load P, or if we can keep the load fixed, okay, F fixed, if we change the distance AC, if we increase the distance AC gradually, then the value of P will increase. So, BC is fixed, BC here it is constant, if we keep constant, if we only increase the AC, then it will increase the value P, and this principle is used in Presley fiber strength tester. Okay. Here in this Presley tester, we test the bundle strength, and the jaw which we have used in stellometer, the same jaw can be used here. Okay. So, the same jaw which we are used, and here it is the point O is the fulcrum point. Okay. So, here we have seen this is the point fulcrum point C, this point is shown here O, and point B, it is nothing but here this is the point B and O, and the point A, here it changes here. So, this is the, and here mass of the, this is the weight, dead weight, it is fixed, and in this instrument the beam it is little bit inclined, so that the mass slides down gradually, so that the distance OA increases gradually. The beam AB, this is AB is the beam here which is pivoted at O. When B rises, okay, B it is moves up, that means the clamp C also moves up. Okay. This is fixed, this is connected, okay, and this applies the force on the fiber bundle here, because bottom clamp is fixed here, okay, and top clamp is connected with B. So, as the load is sliding down, it is increasing. So, it will apply downward force and this B portion would always like to move upward. So, it will apply force, okay, rise. Initially the beam have a slight inclination, this beam it has slight inclination. So, that once this dead weight is released, its tendency is to slide down, okay. So, it is to few degrees. A heavy rolling weight, it is a rolling weight with a roller, when released, initially it is fixed, when it is released from the catch, the roller it rolls down to the along the beam. Now, as it is rolling down, the force we have seen the way it is increasing. So, gradually the force applied on the fiber bundle will increase and A dash O increases until the fiber breaks. So, it is a heavy mass. So, the arrangement is such, as soon as the fiber breaks, the design is such, this dead weight with the roller arrangement, it will not move further, it will stop immediately, okay. That is the arrangement. As soon as it breaks, it will fall down and immediately it will break, it will stop, and so as it break occur, the arm AO drops, this AO arm immediately will fall, okay, on this platform, and the brake arrangement stops the carriage instantly. So, why is it required to stop the carriage? Because that otherwise it will give a wrong result, and as we have seen from the earlier equation, this P value, that AC value, when that BC is constant, okay, and this F value is constant, BC constant, F value is constant. So, P is actually is measured by measuring the AC value, okay. So, AC is the indicator of the force applied on the fiber. So, that is why if we see this beam is gauged, this is the distance, but this distance is gauged directly the breaking load value, okay. This is the directly, it is the breaking load value, it is gauged. So, the distance A dash O when it is breaking is measured of breaking force, it is a measure of breaking force A dash O. The scale is directly graduated on the beam, here it is directly graduated in terms of say gram per tex, and the length of fiber bundle here it is 0.464 inch, the 0.464 inch at 0 gauge length. Now, let us see at 0 gauge length. So, this is the clamp, this is top clamp, this one is bottom clamp. In bottom clamp, among these two, the fibers are, the bundles are, we are fixed, and 0 gauge, there is no gap. 0, it can work in other, say stereometer can work in 3 millimeter gauge length, here gauge length is 0. So, there is no gap. So, the arrangement is that we the fiber bundles are gripped, that is gripped here. Then after that this excess fibers are cut by knife. So, finally, what we get, this is one jaw, this is another jaw, and the fiber bundle is we do not know the number of fibers and all that. This is the fiber bundle, but here the thing which is known is its the length of the fiber bundle. The length of the fiber bundle is 0.464 inch, which is fixed, because here the jaw is fixed for Presley tester. So, this ensure the length which is equal to 11.78 millimeter. This is the at 0 gauge length, the length of the fiber bundle. Okay. Now, after breakage, suppose it is breaking at load of say x pound, at x pound it is breaking. After breakage we take out the this jaws. So, this jaw will be like this, after breakage this jaws will be separated, this is top jaw, because fiber bundle has broken and fiber bundle will remain like this. This is at with the top jaw and these fibers at the bottom jaw. Okay. Now we have to take out these fibers, we have to take the mass of these fibers. So, from top jaw we have taken the fibers, we have top jaw we have taken the fibers collected, and bottom jaw we have taken the fibers, taken out the fibers, and we have taken all this fiber. And this the mass of the fiber we have taken as say y milligram. So, this is x pound is the pound force is the force of the bundle, breaking force of the bundle, here it is the y milligram is the mass of the bundle. Okay. Now here in Presley index it is the nothing but the breaking load in pound by bundle strength in milligram. So, this is gauged in terms of Presley index. So, Presley index is breaking load in pound and bundle strength in milligram. So, x we have seen pound and y milligram we have seen, and we can convert this Presley index in terms of tensile strength in gram per tex by multiplying by 5.36. Okay. So, Presley index is also it shows the tenacity of fiber bundle, and tensile strength is also it is a gram per tex is the tenacity of fiber bundle, but their relationship is 5.36. Now, let us try to see how this 5.36 value we can achieve. Okay. So, what it is showing, the Presley index, it is nothing but breaking load in pound which is x, and the mass is milligram which is y. Okay. Now, what is the length? 11.76. So, 11.78 millimeter length, the mass is, what is the mass? Y milligram, and if we want to measure the takes of this fiber bundle, so we can measure the takes of 1000 meter. So, for 11.78 millimeter, the mass is y milligram. For 1000 meter, what will be the mass in gram? So, it will be y multiplied by 1000 divided by 11.78 in gram. So, this is coming out to be 84.89 multiplied by y gram. Okay. That means, the mass of this material 1000 meter is this much gram, that is this is the takes value. Okay. Now, coming out to the, now let us see, coming to the stress value, force value, that force is x pound. We have to simply convert the x pound into the gram, that is 453.6 gram force, pound force to gram force. And now, the tenacity in gram per takes will be 450, this multiplied by x pound x, 453.6 multiplied by x divided by 84.89 multiplied by y. That means, x by y actual, it was the Presley index. Now, if we see this value, this is nothing but 5.36 into x by Presley index. So, this is the tenacity. So, this way we can calculate the relationship between the Presley index and the tenacity. Now, one can try. So, for 3 millimeter gauge length, what will be the relationship between Presley index and tensile strength? When in case of 0 gauge length, it is 5.36, what will be the relationship between the Presley index and tensile strength in case of 3 millimeter gauge length? Okay. This we can derive. Okay. The load on the specimen P is proportional to the A dash O, so that the rate of loading is governed by the speed of the rolling. So, speed of the rolling. So, that is why this instrument is neither work on CRE principle nor it is working on the CRL principle. So, if the question is that you explain one method which does not work on neither on the CRE principle nor on the CRL principle. So, that is Presley index, Presley instrument is the example of that. Okay. Like stellometer works on CRL principle, and if we can control the velocity of rolling weight by a specially made device, we can achieve CRL principle. That is basically that is difficult, but in normal case it does not work. Okay. Next is the it is an instrument, it is called Cambridge extensometer. This instrument actually it works on both CRL principle and CRE principle. This is the unique instrument which works in both principle, both constant rate of loading principle and constant rate of elongation principle. Now, the principle is that here it is used for single fiber or fine yarn. It cannot actually test very strong yarn, very fine single fiber with at lower lower braking load, because here the loading is with the help of by extending the spring. Okay. Here S is a helical spring, okay, and force of the in spring we have seen force applied is proportional to the extension. If we increase the extension, then force will increase, okay, and if we increase the extension at a constant rate, the force will increase at constant rate, okay, for spring. G1 and G2 are the specimen grips. So, red color this is the actually specimen, and at the top jaw, that is G1 top grip, one leaf spring is there, it's one leaf is there, okay, is the upper grip G is connected with the leaf spring. This is a leaf spring which has a restricted movement between two electrical connects C1 and C2. Okay. This is the leaf spring horizontal, and between C1 and C2 this can move, and the distance between C1 and C2 are very small. Okay. Now, when it is working in CRL condition, constant rate of loading condition. Now, what happens in constant rate of loading condition, and these two screw rods, okay, connected with the follower H1 and H2, the rods that are. So, this rod is driven by motor M1 and other rod is driven by motor M2, and this follower H1 is connected with this rod and follower H2 is connected with the other rod. When the instrument is supposed to work on CRL principle, in that case the motor M1 rotates continuously and motor M2, its normal case, it will remain stop. Okay. Now, when motor M1 starts moving, the follower H1, so as motor moves, okay, starts, the H1 moves upward, this one moves upward, and this motor is stopped. So, this is the fixed jaw, this jaw is fixed, this is the jaw, it is moving upward. Now, as motor M1 starts, H1 moves upward at constant speed, then the spring gets extended. So, as the spring gets extended at constant speed, that means loading will increase at constant rate. Okay. So, at constant rate spring is extending, that means the loading on the specimen is extending at increasing at constant rate. As the extension of the specimen, so as the load is applied on the specimen between G1 and J2, so as the specimen get extended, that means this leaf spring will be in contact with C2 upper restrictor, which is connected with the motor M2. As soon as this there is a connection, there is a it is touching, the motor M2 will get signal and it will start moving downward. That means, H2 will start moving downward, so that again till there is a disconnection, and when it is moving downward, again leaf spring will move little bit downward. So, there will be again it will be disconnected, motor will immediately stop, but the motor M1 rotates continuously, it is rotating continuously, it is moving upward. Okay. So, the extension of the specimen will cause the leaf spring to touch the upper contact C2, which starts the motor M2 and H2 moves downward for the short period. This cycle continues until the specimen breaks. So, this for very short time it will move and again it will stop. Okay. So, this will continue till the it breaks. So, what happens? What is there here? The movement of the H1, the movement of the motor is the indicator of the load here, and movement of the this M2 is the indicator of extension. So, as this motor M1 is moving at constant rate, so it is applying the load at constant rate. So, when it is working in the principle of CRE principle, constant rate of elongation principle, in that case the things will be just reversed. The motor M2 will run continuously and motor M1 only will start and stop intermittently, as we have discussed earlier in case of CRL principle. Okay. So, that is why this motor M1 will run and stop intermittently. So, as the motor M2 moves continuously, so H1 will move down continuously. So, there will be a continuous at constant it will extend at constant rate. So, that is why this process is constant rate of elongation. Now, how to record? So, we can record the load elongation curve. Here in the CRL principle, a chart is mounted on vertical cylinder and the movement of H1, that is movement of H1, that there is a it is recorded by a pen. Okay. So, that the chart is mounted, suppose chart is mounted on a cylinder and cylinder is getting drive from the motor, circular motion it is getting from the motor M2. Okay. And the pen is fixed on, suppose on the H1. So, vertical movement of the pen which show it is basically it shows the load. The movement of H1 measures the load, therefore, the pen moves vertically along with the H1 and the rotation of the cylinder, the actual chart is mounted on a cylinder, vertical cylinder. The rotation of this cylinder will actually show the extension of the material. So, if we make a cylinder like this, suppose this is a cylinder. Okay. Now, here it is the graph paper is there, we are placing graph paper. Now, the rotational speed, rotation is getting from by M2, M2 is giving the rotational motion and the vertical motion is given by the M1. So, M2 is moving when there is extension and loading is there when it is a vertical motion. So, ultimately the resultant there will be a total plot of load elongation plot. So, this will give us the load elongation curve for constant rate of loading. the motor M2 which runs only when the specimen is extended is taken up, and also it rotates the chart cylinder, the angular movement of the cylinder being proportional to the extension. And in case of CRE principle, we can similarly we can get plot. Now, the next principle is that constant, that it is a constant rate of, it works on constant rate of loading principle, and this principle is known as inclined plane principle. Okay. The plane dB, okay. What is the plane? This is the dB is the plane. It is tilted by dropping B at a constant rate. So, there is a, we can, it can be dropped at constant rate, and there is a carriage here which is actually responsible for loading. It is a weighted carriage, okay, of mass W. Now, this side, it is a B side, is dropped at constant rate, we can control by say any arrangement like rack pinion arrangement or by screw arrangement. The plane dB is tilted by dropping B at constant rate. So, here if we see the P is the force applied on the material, on specimen, is equal to W is the mass of the carriage. Okay. This is the W mass. So, W sin theta. So, as the sin theta increases, the W, the P will increase for a same mass. So, P is proportional to sin theta here, W is known. So, if we can change the loading, that increase in sin theta at constant rate, then we can achieve the constant rate of loading. So, P is the loading on the load on the specimen. Now, if we see the triangle here, triangle, the K is the fulcrum point, KAB, it is a triangle where this is the theta is the angle, AKB is the angle theta, which changes, which increases with the dropping of the point B, and if that is the sin theta is proportional to AB, that is this AB, where KB is constant, this is fulcrum point is constant, this beam length KB length is constant. So, this sin theta is proportional to AB here. Now, if we can change, if it is dropping at constant rate, so AB is changing at constant rate, so sin theta is changing at constant rate. So, we are achieving the CRL condition. If AB is increased at a constant rate, sin theta will also increase at constant rate. So, CRL condition is achieved. So, this principle we achieve CRL principle, and here one arrangement is there, this side B, it is simply placed on a platform here, it is not fixed, because as it is sliding, it is at that it is moving down, inclination is increasing, this B point, this point of contact will little bit slide left side, towards left side, that there will be simply sliding. Okay. That is why it is not fixed, it is only placed this end is only placed on that the platform. Okay. So, sin theta is AB that we have discussed, AB by KB. Now, it is moving down. Now, you can see this is not, this little bit it slides. Okay. It is moving down, and the carriage is little bit coming on the right side, it is getting extended, load is increasing at the constant rate, and then it breaks. At that point, as soon as it breaks, we have to stop the machine, and then we can calculate the breaking load. Okay. Next principle is that ballistic or impact principle. Here there is a pendulum, okay, and the specimen is connected with jaw 1, J1 and J2. This is the specimen, okay. And after that this pendulum is actually lifted to the horizontal point here, and with the height h1, and when it is released, pendulum will actually try to move, okay, to reach to other point. When it is lifted, the potential energy is actually stored here. Then with the and this is the height, it is when with the material, with the specimen attached, it has reached the height up to h2, but otherwise if there is no material, it should reach at the other side. So, the potential energy was the up to the height h1. Okay. So, it measures the work of rupture, okay, what is the work done of the specimen instead of maximum breaking force. So, in this principle we can measure the work of rupture, okay. It does not measure the breaking force. Now, you can see the animation here. So, in the first step, when there is no material, okay, without material we are trying to test. Now, it is coming down, free swing is there. So, the pendulum is swinging, ideally it should swing up to the extreme point. Okay. This is the free swing. Okay. Now, we have fixed the material. Okay. When the specimen is attached to the pendulum and it begins to pull the material for breaking. Okay. Now again the pendulum is lifted here, and now we have to release the pendulum. The pendulum is being released here, okay, and pendulum is moving along with the yarn, which is fixed at one fixed jaw, and now the yarn is getting extended. And after breakage, the pendulum will not move up to that point, initial point. Now, after breakage, the pendulum will not reach up to that point, initial point. It will stop somewhere, and that height is now this is the height h 2. Okay. This h 2 height. So, now break the specimen at the position which is h 1 and that at the position T, point T, and the work of rupture we can calculate the W multiplied by h 1 minus h 2, that is the work of rupture. What is the work required to rupture the material? Okay. So, initial work was there, initial energy was there, and up to this energy it is going. So, that is why we can calculate the work of rupture. So, the potential energy at point 1 is W h 1. So, when pendulum is released, it swings down. When it is nearly vertical, it begins to pull the specimen at 2 point. So, here it will start pulling the material and breaks the specimen, and after breaking it rising to the position of the 3 at the point 3. So, from there we can calculate the work of rupture, and K is known to be the center of percussion. So, this is the K of the pendulum. So, what is the importance of center of percussion is that it is the point where there will not be excess jerk on the other side, on the handle. Like in a cricket bat, the point of percussion is the point where the batsman will feel the least jerk. Okay. So, that is the point here. So, that point it is actually connected, because otherwise pendulum will have different uneven movement. Okay. To eliminate that uneven movement, we have to fix the pendulum at that point. Now, strain gauge principle. The strain gauge principle, here most of the modern machines they work in strain gauge principle. The strain gauge actually here the movement of the other jaw is almost negligible. So, that is why we can term this movement, this actual principle as CRE principle, because whatever movement is there it is negligible. Here it is shown, although it is bent, but this bending is very negligible. Okay. In most of the modern tensile testing machine, they work in this principle. Okay. When the beam bends, okay, this beam bends, it has got 3 layers: layer, upper layer, middle layer, and bottom layer. Okay. For any bending, the top layer gets extended and bottom layer gets contracted, and middle layer there is no change. Okay. So, it remains unchanged. Then how to convert this value? So, here what happened in the top layer and bottom layer, that the resistance wires are fixed. Okay. Now, we want to that the deflection, whatever deflection due to the load we want to measure. So, how to convert this value of change in resistance to the load value? Okay. So, that resistance changes due to the extension and contraction of the resistance. So, this is done by the Wheatstone bridge. 2 resistance wires are placed on upper layer, these are the 2 resistance, and other 2 are on the lower side. Upper surface is 2, lower surface there are 2 resistance, and which forms the Wheatstone bridge with the beam undeflected that is when the beam is not deflected, no voltage across CD, there is no voltage. So, it will not show any voltage, and when a voltage applied across AB. So, across AB the input voltage, so there will not be any output voltage because the Wheatstone bridge is balanced. When load is applied, the beam will get deflected and the resistance value will change, okay. And there will be output voltage across CD, and this CD value, this voltage value here is proportional to the load value. Whatever load is applied on the specimen, this will be measured by this application, this output voltage value. Okay. So, the main advantages of this instrument machine is that it is free from inertia. So, we have seen in other machine, other techniques like your pendulum technique or many other technique, the inertia effect is there. This is actually free from inertia, and the deflection of the end of the beam is very, very small. It is we can neglect that one. Thus, the tester, this is tested under CRE condition. Although there will be deflection, if there is no deflection, the load value cannot be measured, but this deflection is negligible. Okay. And this technique is, this principle is versatile. Here we can test yarn, fiber, fabric at wide speed limit and with wide load range. So, that is why this principle, this strain gauge principle is used for most of the modern textile, modern tensile tester with a wide range of load requirement. Main disadvantage of this system is that it requires expert technician, because lots of electronics are there. Chances of drift in electronic circuit. So, okay. So, after repeated extension, repeated loading, the resistance wires may get extended permanently or contracted. So, that may lead to wrong results. That is why this type of instruments need recalibration with after specific interval, and another disadvantage is that its cost is very high. So, in the next segment we will discuss few other techniques. So, like constant rate of winding tester. So, that we will discuss in the next class. So, till then, bye, thank you.